So we've got question 1 on refraction. Light refracts through a thick glass vase, or vase, depending where you're from, how you'll say it, with water in it. It's placed near a window. I guess that's where the light's coming from. The diagram below shows a ray of light travelling through the water. So it's come from outside the vase and has gone in, and now it's travelling through the water, and then travels through the glass and into the air. Complete the diagram to show how the ray is refracted at these two boundaries, the water, glass, air one. So the refractive index of water being lower than the refractive index of glass means it's going to bend away from the normal. So we're going to have to put the normal into, sorry, I've got that back to front. It's going to bend towards the normal because glass is higher refractive index. There's one normal in place. So bending towards the normal, the original line would have passed through straight through like that, so we're going to bend it inwards like that. And then we've got another normal here, and we're going from glass into air. Now air is a lower refractive index, so here's where it would have gone, but we're going to bend away from the normal, so that's where it goes. Let's put arrows on the correct rays so that we're certain about what we've drawn here. Okay, so just to make that absolutely clear, at this boundary it's going to bend towards the normal because the refractive index of glass is greater than the refractive index of water. And then at this boundary it's going to bend away from the normal because the refractive index of air, this is the direction where it's going to, is much smaller than the refractive index of glass and water, but glass is the main issue there. Now very often in these situations people forget about the thickness of the glass and they deal with your vase with your water in it, and they just look at water and air, and they ignore that the glass itself has thickness, and so we have to consider that in the whole process too. Anyway, moving on, next question. Explain why refraction takes place at the interfaces, as shown by your sketch in the completed diagram above. So our explanation why refraction takes place at the interfaces is because there are different refractive indexes, and light is passing at an angle from one to the other. Okay, so that's not a lengthy explanation, but it's getting into the heart of this. Refraction, but yeah, basically going through it again, refraction takes place at the first interface because you've got water and glass are different substances with different refractive indexes, and it bends towards the normal because glass has a higher refractive index than water. Refractive index takes place at the next interface because glass and air have different refractive indexes, with glass being higher than air in this case. And so it's going from a high to a low, whereas previously it was going from a low to a high, and so the bending will go in a different direction. Now if it didn't hit on an angle, if it hit straight through, there would be no refraction. So it's important to include that idea of the angle, the different refractive indexes, and that it's actually travelling from one to the other. Okay, moving on. C. I would just like to note, this question above doesn't explain, doesn't get into how refraction actually works. And I'm not sure, it doesn't explain, I'm not sure if anyone thoroughly knows, but it's an observed phenomena which occurs under those conditions. So we're just describing the conditions, we're not actually describing how they work. That's interesting, but that's how we deal with those questions. So next one. Bicycle reflectors are made from plastic and have prisms to reflect light back in the direction from which it came. The ray diagram below shows how a bicycle reflector reflects light. So we can see we've got the incoming ray, and then total internal reflection. This is probably where it's going to go, but total internal reflection occurs at this point, and same at this point, and then it carries on out in that direction. So it's reflected, reflects it parallel to the incoming ray but in the opposite direction. So use physics ideas to explain why the prism in the bicycle reflector reflects light back in the direction from which it came, as shown on the diagram. Okay, that's exactly what it's getting at. But if we're getting more specific, more detailed, we'll talk about the angle of incidence, which is, I'll try and draw it down here. The angle of incidence is, I'll colour it in because that's easier than trying to, right there, is greater than the critical angle. Remember, the critical angle is the angle beyond which total internal reflection will occur. So the incident angle is greater than that, which means total internal reflection occurs, and it does that not only at the one spot but also at the second spot. Okay, have we covered everything there? Yes, I think that's a pretty clear answer. A lot of space to write all that down, but D. When white light passes through a glass prism, it disperses to produce a spectrum of 7 colours. The table next to the diagram shows the positions of the red and blue light in the spectrum. On the diagram above, write down the relative positions of yellow, green and violet colours. Well, remember it's Roy, red, orange, yellow, green, blue and violet, or indigo if you want to, and violet. What are we after? We're after yellow. Let's write yellow in yellow just for fun. In fact, let's colour them in. Let's thoroughly colour them in if I've got enough colours here. So we've got red first, orange, there's no gaps in between them, but it's yellow, green, blue, and I don't really know what colour we have for indigo. I guess it's somewhere between. Let's do it. We'll represent it this way. So I'll draw sort of a shaded purple, and then we've got a dark purple or violet for the. There we go. So that's our violet, that's what they're asking for. Green is what they're asking for there, and yellow is also asking for it. Looks pretty. Lots of colours are good. Okay, now here's the big one, the last one. Explain why the blue light ray is refracted more than red when entering the glass. Well, again, same thing, we don't exactly know why refraction occurs, but if we're talking about why the blue ray is refracted more than red, we would talk about the glass actually has a refractive index which is different for each wavelength of light. And so the refractive index is for the blue is actually going to be greater than the refractive index for the red. And so it'll bend more, because remember, the greater the refractive index, the greater the bending. So yeah, I think that covers it. I'll just double check on the schedule for you to make sure I've covered it all. Yep. Another way of looking at it could be to look at the speed of light, because remember, when you go to a higher optical density substance, the speed of light will decrease, and it decreases by a different amount for different refractive index. So yeah, in this case, blue light would slow down more. Yep, that's correct. Blue light slows down more, so it'll bend more. And yeah, it's also the same reason why we see a blue sky, because blue light bends more. That's why we only see the sun. So the sunset is red and orange and all those lovely colours when the sun is close to the horizon, so when it's rising or setting. Otherwise we just see the blue, which is bent the most, and so we see the most of it. The rest of it is scattered back out into space. It's like a raindrop with all of the light that's sort of coming in and scattering, and then you don't see all of it. Yeah, the blue does. Anyway, you get the idea. You can have a play with that idea for yourself. Cool. Fantastic.